Great. The story of Newman Projections continues to unfold and will be brought to its conclusion in this film. Looking back at some of my files here, see, we first started to reconcile from point of view wedge or hashes from a point of view taking us up, down, left, or right. And from there, we came to know a spoke carbon as the carbon in the front and a sphere carbon as a carbon in the back. Add that to your collection of carbons from endpoints, vertexes, and junctions. And then we can find the total number of carbon atoms in a Newman projection. And we did another example at the time. You didn't know it, but this was turning out to be an eclipsed conformation for a Newman projection. It was an eclipsed conformation. And then we had a series of definitions: the dihedral angle, the torsional strain, the steric strain, anti-conformation, partly eclipsed conformation, gauche conformation, 60 degrees, fully eclipsed conformation, 0 degrees in terms of dihedral angles, and respectively in order of decreasing stability, most stable first. You could rank those conformations appropriately. And we even had a problem where can you determine which molecule is identical to the other based on Newman projections. And so we've been approaching this a lot of different ways, drawing Newman projections from scratch, learning definitions, ranking conformations, line angle formula, how that feeds into this. This is a lot of different working gears, like you'd find in the workings of a clock, a lot of moving parts here. And so the last part we would have to cover is for any alkane name of a molecule, could you come up with the most stable? I'm thinking staggered anti, and the least stable, I'm thinking totally eclipsed conformation or shape of that given molecule. So we'll be doing 2 problems and 2 problems only towards this end. Yeah. Okay, so this is the capstone for Newman projections. Welcome. So our directions are number 12. We're going to write Newman projections as to the spokes and spheres for the following unique, well, it says branched here, but this first one isn't branched. So if I could strike that or remove that, I could. If I could make another pass revision at this handout, but the following alkanes. And what's important, if you will notice, please, is that each and every time the lowest energy conformation will be that of anti, if possible, or staggered. I might come back and revisit that and say anti or staggered. Whatever, not eclipsed, right? Not eclipsed. Whereas when we go to draw the highest energy conformation, as I've already set this up here, it's going to be eclipsed, probably totally eclipsed, where we overlap on purposefully, the bulkiest groups. Eclipse or overlap, however you like. Eclipse, overlap the bulkiest groups. That's what we're seeking to do, to make to come up with the most unstable conformation. Okay, so we're looking at heptane, not hexane, heptane. So we're going to want to come up with, I named it left and right, but you can also name it spoke and sphere carbons. So the groups attached to the spoke and the groups attached to the sphere. we're going to do problems A and C. So I'll set us up for that. Sometimes you'll see left and right, but you can say spoke and sphere. We'll have the spoke beyond the left and the sphere beyond the right. And you can do vice versa. It's up to you, but it has to be internally consistent. So, and we'll zoom in here on this problem. So if I may, and pencil. I highlighted this bond in red. It's a very special bond along which the rotations occur. This made hexane, one more makes heptane. Heptane already. So we're thinking about rotating this molecule along. See how I'm flexing this? Let me stop sharing perhaps. We're rotating this molecule along these red atoms because single bonds are flexible to come up with the most and least stable conformation. So this is going to be the spoke carbon. Slide these over here. Spoke is to the left, sphere is to the right. The pegs, okay? Spoke, peg, sphere, peg. Sphere, peg. So what groups do you see attached to the spoke vertex? Be careful how you circle this, okay? I want to circle this like that to bisect, B-I-C-E-C-T, B-I-S-E-C-T, to bisect the bond. This is not good to circle like this. This is going to lead to mistakes. Not good. Don't do it like that. Not good. Don't do it like that. I'm going to circle two carbons. That's good. That's an ethyl group. Okay. What else is attached to this spoke carbon on the left? According to line angle formula, two hydrogens. So it goes ethyl, hydrogen, hydrogen. You can make a note of that. Ethyl, hydrogen, hydrogen. And the same game is played for the right. Again, if you circle like this is going to lead to mistakes. Mistakes you don't want and I don't want. So don't circle. You want to bisect the bond right off of the peg chip. That's it. How many carbons are in that red oval? 3. 3. So that's N-propyl, NPR. And what else? A hydrogen and a hydrogen. Those are our groups. All consistent. Now we just have to assemble this information in a Newman projection. Anti or staggered. We put these in all at once. Okay, so let's and let's purposefully put these on spokes. Okay, you have to pay attention. Okay, you have to put the ethyl, the hydrogen on spoke carbons. Okay, so pay attention. It doesn't matter where you put them. It's your choice. Ethyl, it has to be in a spoke. Okay, on the spoke, on the longer ones. And most stable, lowest energy. I'm going to put the N-propyl here. That way it's further apart from that bulky ethyl. Hydrogen, hydrogen. This is as stable as it gets for heptane to have the ethyl piece 180 degrees apart from the N-propyl piece. Another way to draw this, if you want the line angle formula version, is as such. I'm satisfied with the abbreviations. Abbreviations are fine. The ET, IPR, so forth. I'm going to do NPR or N-propyl below. So 1, 2, 3. The same thing. That's the same thing, everybody. That's as good as it gets. 180 degrees apart. There's no torsion. There's no sterics. Perfect. Low energy, low strain, stable. 45 out of every 100 molecules will likely exist like that at any point in time. So if I, again, pay attention to put the ethyl, because I've had students before put the ethyl, they don't mean to, but they put it on, they'll put the ethyl and the N-propyl on both on the spoke. That's not good, That's not good, So the ethyl has to be in the spoke, and because the N-propyl is on the other peg chip, you have to put that on the sphere. So how can I make this situation highest energy, most unpleasant as possible? Well, why don't we just jam them in? And that way that they can feel each other's bulk. They can get stressed out with the sterics. This is not a very stable conformation. Only 10 molecules out of every 100 will exist like this. So you want to kind of smack up against, superimpose the ethyl and the N-propyl. So, and that would look like this. This is eclipsed, one and all. That is eclipsed. And if I swing this gigantic N-propyl around, get ready to hear it. Clank, clank, clank. Sterics. And these electrons and the bonds I'm touching really are feeling this repulsive force. They want to get away from each other. Molecules kind of tearing itself apart at this time. The bonds are stressed out, pent up, strain, high energy. So it's not a good situation, but that would be the most, it's allowed to exist, but that's the most unstable conformation on record. And it can also be drawn. This is good enough for me, but if you want to draw it alternatively, you can draw it like this. And then we'll have one more column left to do. So there's the ethyl. Instead of ET, I wrote out the line angle formula, vertex, endpoint, and here's the N-propyl. I dare you to fit that in there. That was tough. That was tough to fit in. I'm not satisfied with that, actually. So a little bit better. Well, that's what you're seeing right here, right now. That's kind of what you're seeing at this point. Yeah. Yep. Now what you're seeing, I just drew it for you. I put in the H's. Yeah. So either the abbreviations or the line angle formulas are good. And please note how N-propyl, as I type to summarize here, N-propyl is on the sphere and ethyl is on the spoke. So it will not be that ethyl and N-propyl are both on the spoke. You need to pay attention. Okay. All right. And for C. So problem B will be very much like problem A. We have a T-butyl group, hydrogen and a hydrogen. On the right, you'll have an isobutyl group, a hydrogen and a hydrogen. I wasn't going to go through this, but I can. Hydrogen, the hydrogen, and the T-butyl, and likewise for the isobutyl. So that's why you want to know your alkyl groups. That's the T-butyl. That was on the left. Well, likewise, we'll assemble a list here for the spoke and the sphere. C left and C right. We're going to highlight the bond. and see if you can come up with these. Okay, so left peg, if it helps you. And this is our last problem. And congratulations for making it this far. This was a time investment on your part to make it this far. So, yep. Think about the time investment. So I give each of you credit for seeing this through. I give each of you credit for making it this far. And where necessary, rewatching certain parts of the video, feel free to come to office hours for clarifications. Always feel free. Maybe the molecule really quickly, I think. Nope. Here we kind of have it. Left peg with two methyl groups, right peg with an isopropyl group. Okay. You see all the different shapes this can assume. So this problem's kind of different because we have a spoke with two groups on it, two alkyl groups, whereas before it was spoke had one alkyl group, sphere had one alkyl group. So this is kind of different. That's why we're doing this problem. So let's dedicate a hydrogen here, and that can help us complete our list for the peg chip. On the left, we have methyl, methyl, hydrogen. I'll help you see it, of course. Methyl group, circle the end of it. Methyl group, circle the end of it. Hydrogen. And on the right, this has two hydrogens on it. That peg chip has two hydrogens. And what is this group? As I may have referred to earlier, it's an isopropyl. So isopropyl, hydrogen, hydrogen. That's what we're going to assemble. So partial credit is building. So we do have to pay attention again, okay? So the methyl, and the hydrogen are going to go on the spoke, okay? You have to pay attention here. Be alert. Pay attention. It doesn't matter where you would dedicate that to. So I'm just going to put it here. Methyl on the bottom. You could put the methyl on the top and the methyl on the right. It doesn't matter. So, and we have a hydrogen there. What we're trying to do here is get the lowest energy conformation. I don't think putting the isopropyl here would be very good. Do you? Because there will be smacks, clashes, maybe a lot of sterics. So why don't instead we put the isopropyl in between that of a methyl and a hydrogen? A little more roomy, okay? A little more room for this big bulky isopropyl group. That's good. And we have two hydrogens there. So where to seat the isopropyl? Why don't we put the isopropyl between a hydrogen and a methyl? Now I'm drawing it in line angle formula. Keep in mind the size of that hydrogen atom. It's very small, only one proton. A carbon has itself 6 protons, so much, much larger, even though I have to draw out a capital H. So that's kind of, but I will, yeah. Symbology kind of interferes with understanding, perhaps. But it's supposed to be a circle there. So fill that in, perhaps. Okay, much better. Looks pretty good, doesn't it? So you can see how bad that would be if we put a 6 carbon methyl CH3, excuse me, a 1 carbon methyl CH3 with 6 protons for carbon. A lot of sterics there. Now it even looks worse. So that's not as good, not as stable. All the hydrogens above. That's not as good. That wouldn't have been as good. So it's best to put the isopropyl in between, not, nope, not in between the methyl and the methyl, but in between the methyl and the hydrogen. Okay, all right. And now to get the most, to get the worst situation, again, let's pay attention here. Methyl on the spoke, methyl on the spoke, and hydrogen on the spoke. And where can I put the isopropyl to cause the most damage, to cause the most sterics? Well, it wouldn't be that bad. I want to make the most. Okay, I'm going to make it the worst case scenario, isopropyl here, overlapping a methyl, eclipsing it, or eclipsed by a methyl eclipsing isopropyl. This is the answer. It's the worst possible situation. I'll try to draw it down here. You can see how unstable it is a little bit better. I'll also draw it like that. Line angle formula. I have to break the bond to show that that's in the back. Nice, huh? Well, not too bad. Have to pay attention to what I'm doing. Does my spoke have two methyls? Yes. Does my sphere have two hydrogens? Yes. That's good. That's not too good, huh? That's eclipsed. And what you're looking at is this. Right? Yeah, that's what you're looking at. I just drew it. This methyl group here is eclipsing, I turn it like that, the isopropyl group. I'm touching methyl. Having a hard time seeing the isopropyl group, aren't you? Here's the isopropyl group, carbon, carbon, carbon. Methyl right in front of it. This is fully eclipsed. Okay, so I hope you find success with problems along those lines. This was to complete the circuit for Newman projections, and circuit completed. Film 4 complete. Topic met. Good dedication. Thank you for tuning in.